Welcome back. We're going to keep working with engine dimensions, but now explore um, the more advanced topic of compression ratio and how to calculate that. So in general, before we start in, I want to give you sort of the big picture of what we're talking about here. Any kind of fuel can only be squeezed so much before it'll self-ignite. So an engine has to be designed to squeeze the amount of fuel into a smaller space, not too much. If it compresses it too much, it'll ignite too soon. But if it doesn't compress it enough, then it doesn't get all the power and it's not efficient. So we kind of want to get that squeezing ability just right. And the measure of how much that fuel gets squeezed, that's called our compression ratio. So in the picture that's shown here, we can use any units to find compression ratio. We'll usually use cubic inches, but we'll use cc's for an example as well. Whatever those units are, they just need to match. And if we take 16 units or 16 blocks of air and fuel and squeeze it into 1 unit or 1 block in fuel, then we would say that the compression ratio here is 16 to 1. 16 to 1 is a pretty common compression ratio for diesel fuel. Gasoline engines can't be squeezed quite that much. So there's going to be a few formulas in this section. These should go on your gold sheet or on your temporary formula sheet. Here's the first and most important one. Compression ratio is the measure of the volume at bottom dead center. That is to say, when the piston is all the way down in its cylinder, it's that volume divided by the volume at top dead center, which is this volume right here. Our goal in this section will be to calculate what these volumes are so that we can divide them to compute the compression ratio. Now, a little bit of history. Henry Ford's early Model Ts had a compression ratio of about 4.5 to 1. That is to say, they only squeezed air and fuel about 4 or 5 times. So it might only squeeze 5 units of air, or about 4.5, into 1 unit of space. That's not much compression, but that's why these early engines only made about 20 horsepower. The other reason that compression ratios had to stay fairly low is, of course, how did these early engines start? They had a crank on the front and you had to crank them by hand. So any squeezing that occurred in those cylinders had to happen through muscle that the driver or starter could provide, and that wasn't very much, so compression ratios were kept low. So before we get into the math, I want to extend the background a little bit more here. Typical gasoline engines typically have about a 9 to 1 compression ratio, and that's pretty normal for about 87 octane fuel. Octane is a measure of how much that fuel can be squeezed before it's going to detonate or ignite on its own. Now, if we go up to about a 92 octane fuel, that means that that fuel is a little bit more squeezable. It can handle some higher temperatures. Those engines are up around 10 to 1. And again, these aren't strict rules, but approximations. It depends a lot on engine temperature and your engine timing, what kind of load the engine is under, so a lot of other factors. But gasoline around 9 or 10 to 1 for the typical range of pump gas. Diesel engines, the diesel fuel can be squeezed more. Since diesel fuel is less volatile or a little bit less explosive, it can be squeezed a little bit more. 15 to 22 to 1 is typical. And for propane engines, their octane rating is around 106 to 110. That's in the neighborhood of like racing fuel. And racing fuel and LP, they can both be squeezed about 13 to 1. So as we're working through problems for today, this sort of gives you an idea of what to expect. Anytime we're working with a gasoline engine, we better get a compression ratio somewhere around 9 or 10 to 1. If we're working with a diesel engine, you can expect somewhere in the neighborhood of 15 or 20 to 1. And we've got a couple, you might have some homework problems with some racing engines. Racing engines where you're burning racing fuel, they might be anywhere from 12 to 13 to 1. So let's start building the math that we need to calculate this. You need to be familiar with 5 key volumes that exist within the engine. We're going to go through these from top to bottom. The first volume is this top volume. Volume number 1 is your combustion chamber. Sometimes this is kind of casually called the cylinder head volume or simply the head volume. And that is almost always given to you because that's mathematically very difficult to compute. And it's usually given in cc's. Below your cylinder head, hopefully, your engine has a head gasket installed. And that ring, that space, has some volume to it. And so our second volume is the head gasket volume. That's a volume that we can compute, and we'll see how to do that a little bit later. Now the third volume is hard to see on this picture, but the piston doesn't actually go all the way to the top of the block. And there's a few reasons for that. One of them, the main one, is so that if the block needs to be machined, the piston doesn't stick out. But there's a third volume right below the head gasket, and that's called our deck volume. Sometimes you'll see that called your piston to deck volume. And that's another one that we can compute. Now at the bottom of this picture, we have this volume right here, and it's not very big, but there's some piston relief right there. That is volume number 4, your piston relief volume. You can be writing these down on your gold formula sheet. We don't have too many more formulas in the class. Or you can write these on your temporary sheet. The piston relief volume, by the way, is sometimes called the piston dish. Now, all 4 of those are always present inside the cylinder. No matter where the piston is, these 4 are always present. But there's a 5th one that's not always present, and that is the main volume inside the cylinder. That is to say, that volume comes and goes depending on whether the piston is at the top or the bottom. And that is, of course, we just saw that in our last topic, that's called your swept volume. And the swept volume is only there when the piston's at bottom dead center. At top dead center, it disappears. So I want you to pause the video and study this just a little bit. Understanding these 5 volumes are essential to go forward anymore. At the top of our cylinder, we have the combustion chamber volume. That is to say, the volume within our cylinder head that we bolt onto the top of the engine. Below that, there's a little bit of volume in the head gasket between the block and the head. Below that, we have a deck volume, or piston to deck volume, and that's just the space. It's hard to see in this picture, but that's the space above the piston, even when the piston's at top dead center. Just a little bit of space up above the piston, but below the top of the block, but we have to be able to measure that. Our 4th of the always there volumes is the piston relief, and again, that's any dish that the piston might have. Some pistons are domed, but we're not going to deal with that in this video. And then the 5th volume, the one that's sometimes there, the one that actually comes and goes when the engine is running, that is our swept volume. Okay, once you feel like you understand and agree with those 5 volumes, then you can proceed as we start to get mathematical about this. Okay, those 4 volumes that are always there, those are called the clearance volume. If you take your combustion chamber, your piston dish, your head gasket volume, and the deck volume and add all those up, those are called your clearance volume. So those are these 4 volumes up above. The clearance volume is always there. That is the volume at top dead center. If you think about it, when the piston goes all the way up, all the air and fuel is in these 4 volumes. That is our top dead center formula. We need that for calculating compression ratio. So then to actually find the compression ratio, this is the formula we use. If we have the swept volume, number 5, plus the clearance volume, those are all 5 volumes combined. That top number there, that is our bottom dead center volume. Whereas the clearance volume, that's where the air and fuel gets stuffed. That is our top dead center volume. And that is the formula that we saw earlier on. So this right here is the formula. These 2 formulas are the ones that we actually use to calculate compression ratio. First, we find the clearance volume by adding up those 4 small ones. And then once we know the clearance volume, We plug that in along with our swept volume, and that allows us to calculate compression ratio, which is the second part of calculating compression ratio. So let's take a look at an example. Okay, a Chevy 5.3 liter, it's a common truck engine, has the following specs, and the question is, what is the compression ratio? So the combustion chambers, that is volume number 1. At the top of our cylinder, 58 cc's. Below that is our gasket, that's volume number 2. Below that is our deck, that's volume number 3. The piston relief, that's volume number 4. And then our final volume, the one that comes and goes, number 5 is our swept volume. The first thing to notice here, though, is that our units are mismatched. It's always true with compression ratio. You can use any units you want, but they must match. So we have a little converting to do. Let's take our combustion chambers and convert those into cubic inches to match everything else. So let's put 58 cc's over 1. We're going to use this fact again. 16.39 cc's is equal to 1 cubic inch. We used that in the last topic as well. And 2 decimals is fine here. 3.54 cubic inches is our combustion chamber volume. Gasket volume, that's in cubic inches, it's okay. Deck volume, that's in cubic inches, those are both okay. Piston relief, 12 cc's. Whoops, we better convert that over as well. So 12 cc's, we're going to divide that by 16.39 cc's per cubic inch. And we get 0.73 cubic inches. There, now that's in cubic inches, and we're in good shape. Okay, so since our swept volume is also in cubic inches, we're ready to go. First of all, what is our clearance volume? Our clearance volume are the 4 small ones added together. Our combustion chamber volume, plus our gasket volume, plus our deck volume, plus our piston relief, and that gives us 4.73. It's important to note that those are cubic inches. So we found our clearance volume. All the air and fuel in this engine gets jammed into 4.73 cubic inches. Now we can go ahead and find our compression ratio. Just a refresher here, we're going to take the swept volume, we're going to add on the clearance volume, and then we're going to divide those. Make sure that you put parentheses around there or get that total first. And then we'll divide by our clearance volume. Let's go ahead and do that. And so our swept volume is 40.62 cubic inches plus our clearance volume of 4.73 cubic inches. And we're going to divide that by 4.73 cubic inches. Make sure you get that total in the numerator first. And that gives us 45.35 cubic inches divided by 4.73 cubic inches. Now when you divide that, the units cancel, as is often the case, and we end up with 9.6, and that's a ratio, so 9.6 to 1. And we always round to 1 decimal on compression ratios. Always 2 decimals on gear ratios, that's kind of an industry standard. And we always go 1 decimal on compression ratios. We keep 2 on all these calculations before that, just to eliminate rounding error, but we always go to 1 on our final compression ratio. There we go, and we're done. Now, those are the fundamentals of how to find compression ratio. And the C-level problems, the basic problems for this topic, will stop right there.